bottom line is that you have all these gases produced by life. You can actually make a quantitative framework trying to understand how much you need, how does this relate to the amount of bacteria you would need on Earth. And eventually this work will be published and you can read more about it. So that's that. And it was a little disappointing. I really was thinking I could just find a bunch of new biosocial gases. But nonetheless, here it is. We will work through these and see if there's any scenario at all where they can be biosignatures. I'm not going to end on a depressed note. I'll end on another note that if you move beyond these redox gases, and then you say, what other gases does life produce? Not the ones that are using redox reactions to extract energy, but anything at all. And actually, you know what? There's thousands and thousands of them, like tens of thousands of compounds produced by life. The issue here is that they're produced in very small quantities. Think of like when you walk into a pine forest, where you smell a lemon, like all those compounds produced by life can be produced by life. And it's actually, they're in really small quantities. So the trick might be, could you think of one? Or could there be one? Or could you be prepared to find something unusual and complicated? And these, we don't have a better name for them. If you do, you can suggest one. We just call them secondary metabolic byproducts, because they're not produced by microbial life that's trying to extract energy from chemical energy gradients. And I'll give you a couple of examples. Now, in exoplanets, people have used a couple of these already in the literature, randomly so. We try to do a more complete, coherent summary of what's out there. So one is DMS. How many people have heard of DMS, dimethyl sulfide? Few people. It's produced by marine phytoplankton. And it's not, I don't think it's exactly known why it is produced, but it is produced in quite a large volume. You can see here, fluxes of kilograms per year. And what's really interesting is, you know what, it's actually related to global warming, because this DMS goes up there and it ends up making aerosols that end up being seeds for clouds. So actually, it's actually quite known. If you Google DMS, you'll see a lot of stuff about it. It's a well-known thing. And actually, the first paper even considering biosignatures slightly beyond the common terracentric ones was by Carl Pilcher. He's at NASA now, in 2003. He took DMS, and he didn't really make a model, but he said, here's an example. If you had a lot more of it, maybe it could be observable later on. Other people have tried to show that if you have a planet in a system with low UV radiation, it's more likely to accumulate and not go on its path to forming sulfates. So that's one of them. And there are also sulfur compounds. Other people have looked at methyl chloride. Again, so we're trying to summarize. So it turns out there's a lot of these things. Here are a bunch of methylated compounds that are produced by life. And they're also volatile, which means they are in gas form in the atmosphere. And there's this huge list of stuff. And here's a list of other volatile organic compounds. So in fact, there are a huge number of biosignatures on Earth alone that we could try to consider in some other contexts for life elsewhere. But it's a long story of how to do this, and we're still trying to sort through what we can do. So it's a great thing that there are so many compounds produced by life. Everyone looks a little puzzled here. They're all out there. But trying to put them in some kind of framework, I think, is straightforward for redox reaction metabolic byproducts. But for these secondary ones, we don't know why life produces a lot of them and why which ones could be available. But I think it's great that if we can look at an exoplanet and find a gas that just doesn't belong there, we could have some hope of figuring out what it might be like. So I have a few summary slides now, 3 summary slides. The summary for the search for life beyond Earth. The terracentric, this is a summarizing the exoplanet biosignature part. Terracentric unique biosignatures are oxygen and NGO. Ozone is a photochemical byproduct. And I can actually say this with confidence now, having read a lot of literature, textbooks, trying to see what gases are produced by life on Earth and which ones are really truly unique in terms of small molecules produced by chemical energy gradients. And gases produced by life by chemical potential energy gradients include this list here. They're not a huge number of them, and many of them are produced by geophysics or already exist naturally. Gases produced by secondary processes number in the thousands. They're usually in small quantities, but some of them may be able to accumulate. People have shown these 2 examples already in the literature under a planet with a low UV radiation star. And I really think biosignature research is just beginning. I don't know where this is going to go, but in terms of exoplanets and fields that are not really thought through carefully yet, I really believe this one is one of the few areas that is really left to start something really new on it. And that's why I'm excited about it and why I'm working on it. Now, to summarize this talk, these are the main points to walk away with. Earth life is found under a variety of extreme conditions. Almost anywhere you look on Earth that has liquid water, you will find life. And this is really heartening for exoplanets, because we, on exoplanets, can take on a wide range of conditions. Many bodies in the solar system have ingredients for life, and I mentioned 3 of them: search for life on Mars, potential for life in Europa's liquid water, and even Titan that has liquid, right temperature for covalent bonds, and an energy source. Exoplanets will eventually offer us planets with possibilities for remote observations of biosignatures. And the difference from Earth, where we have bodies where we actually could potentially travel to, we're still hoping that an exoplanet, either in this generation or beyond, will have enough planets at your disposal to actually find signs of life on those planets. And I wanted to finish my lecture with a few points about exoplanets. And this captures some of the theme that was beyond scientific, but that I want you to be able to walk away with. And I hope that this message came out clearly many times. And I'll start with the one at the bottom, where the very first thing I said when I started here was, in exoplanets, we want to change the way we see the universe. The great thing now is that any child, any person who's 15 years old or younger, and you ask them, when did they hear about exoplanets? They've always known about exoplanets, because their whole life exoplanets existed. And we want to even take that a step farther, to be able to take people to the dark sky and to tell them that there are planets out there like Earth, and to be able to show them a star where we think there's an Earth-like planet. And there is a growing group of dedicated astronomers and engineers who are going to find these other Earths. And it's going to happen. I really believe this is going to happen, and it's going to change the way that we see the universe. And in exoplanets, my favorite phrase is, anything is possible within the laws of physics and chemistry, simply because of the huge diversity of exoplanets. The range of planets, their masses, orbits, and semi-major axes, and hopefully atmospheric composition is just incredibly, incredibly diverse. So I want to leave you with these three thoughts. And I just want to say again, thanks for hosting my visit. I've had a great time talking to so many people here. Today's my last day. And we have plenty of time for discussion now, and also upstairs in the reception. So thanks for coming to my talk.